Welcome to the second in our series of lectures on systems engineering. In this lecture, we're going to look at product management and building the right product and how that translates to gathering requirements from your stakeholders and understanding the information that you need to build a successful product. My name is Tim Kerby. I run a company called Edinburgh Systems Ltd, and we specialise in bringing systems engineering and product management into technology companies. The first thing we need to consider is how to find the right problems to solve, and this is one of my very favourite quotes from IEEE conference in 1955. Too many products are developed to satisfy the desires, urges and hunches of people within the company, rather than to meet the specific needs of the market external to the company. Products grow out of a desire to tinker or because an engineer sees a purely technical challenge. And this is a critical problem that I see across different industries and different market sectors, that engineers pick the problems that are interesting to solve, not necessarily the problems that matter to their customers and their stakeholders. And we all like to tinker. We all like to play with new technology. We all like to learn, and often the most interesting things are not necessarily the things that the market needs at the time. But when we look at which problems the market does need, there's three key characteristics that we need to consider. The first is that the problem we're trying to solve is pervasive, so multiple stakeholders have that problem at the same time. The second is it's urgent. That means it's needed by the market now, or rather, it's needed by the market at about the time we can deliver that product into the market. There's no point in delivering something too late, particularly if your competitor's likely to have got there first, or delivering something too early to only a small group of early adopters who don't form a large enough sector of that market. But most importantly, it needs to be something that's valuable. That means it's solving a problem that has high value to your customers, to your stakeholders, and is important to them, because if it's important to them and it has value, they will pay you money for it. To give an example here, as a lot of my background has been in electronics and semiconductor, the language that's used in that industry to describe products is usually the product data sheet. And this is an example of how some engagements in the past used to typically go and how they can be done better. So usually someone in a marketing team will go around the different customers and they'll show them a preliminary data sheet of a product that the company has decided it wants to develop. Now, internally, to be fair on them, they've usually looked at various market needs. They've got a good idea of the market because they're skilled in that area, so they've come up with a product that they think would be useful. They'll take that specification out to lots of customers, they'll get some feedback, and those customers will be thinking about how they could use that in some of their own product developments. They'll look at that. There's usually not much more of a conversation other than, yeah, we think they might buy this. And they take away the preliminary data sheet. They maybe don't have much more of a conversation with those stakeholders and customers over time. And as they start to build this product, they realize that they can't meet all of the specifications in the data sheet. So they start crossing things out. They might change features. They may add features where they have lots of different customers, might have different needs, but that makes it a Swiss Army knife product that is not great at doing any of the particular functions. For instance, the package size might get too big for a series of customers because you've had to add in more pins. So they update this data sheet and they evolve this product as they develop it, but they don't often check that it's still solving the customer's problems. So when they come back to the customer, they've got that physical product and they say, how many of these would you like to buy? The customer doesn't buy any. And we see with a lot of electronics companies, this is a large majority of their products fall into this area and they don't sell, they don't make money, and unfortunately, they don't realize why, because they're not closing that feedback loop. So the way this should go is they should be asking the customer about their biggest challenges, why they need the product, and you keep asking the question why. You keep trying to get more information out of that customer. So if they explain something, you want to delve down another level to see what problems are really critical. That allows you to value those problems correctly. So you want to understand what the product is, what the challenges are in their own design, What the challenges are potentially with manufacturing, if there are other components that are impacted by this, if there's any particular requirements have higher value than others to them. And by gathering that data, if your product has to change during the development cycle, then you can evaluate that change against your customer's need, and you can make informed decisions to see whether the customer will still have value for the product and whether they'll still have a need for it. So that's how this should work, and that's how companies are moving towards these product management focused approaches and trying to elicit that data. And that often means not having your marketing staff talking to buyers, but actually getting product managers and engineers talking to engineers and trying to see how those problems apply in the systems and have those real conversations and that information sharing. And that's absolutely critical as well when you move into safety systems, because you need to have that level of trust and that level of understanding of how both systems work to be able to make those systems safe. So some of this, as we've talked about a little there, is a problem between requirements and specifications. So requirements describe a need or a problem in a way that's unambiguous, complete, verifiable, and consistent. So it's talking about things like the system shall be green, the system shall be powered from a 5-volt power supply. It's a series of atomic statements which are very unambiguous and define those customers' needs in a way that's easy for the engineers to understand. Specifications, on the other hand, are a response to requirements. So it's one solution engineered to meet those requirements. It's your outbound information that describe what you're going to build, not necessarily what is needed. So the requirements are really the foundation on which good systems are built. They help us identify the right products to build, they ensure we're building it right, they ensure that ultimately they satisfy that customer need. They're the tool we use to represent stakeholders internally. So with requirements traceability in some of the tools, we can see the impact of any changes and how that impacts the customer system and whether that will ultimately fail to meet the customer's need. Specifications, on the other hand, are outbound information. They detail what the system does. They don't help us decide what to build. So we use those as a communication tool, and in the form of a data sheet, it helps the customer select and integrate that product because it provides them the information that they need to build that into their system correctly. They're not interchangeable. The requirements have to come first here. And we then look at the specifications, and our engineering work is done in converting those requirements, taking them and translating them into the specifications by understanding the trade-offs in the system and deciding which particular components, parameters are the optimal solution to meet those requirements. One key thing is verification and validation have to be carried out against requirements, not specifications, because we are proving that we solve the customer problem, not proving that we have designed what we think we wanted to design internally. And we also want to gather some context on those requirements. So that's supporting information, looking at why they exist, how they were generated, where they came from, any information that can help the understanding of those requirements when someone comes to read them as an engineer later. So one thing I'd like to touch on here as well, which is really critical, is systems thinking. So it's how we look at the system as a whole, rather than as just the component parts. Systems thinking is a way of thinking about that system as a whole. It's looking at interconnected elements rather than the standalone individual components. It helps us understand emergent behavior. So emergent behavior is really what the system does when those parts come together. And it can be positive. So when we take the wheels of a bike, the pedals and a chain, we put them together in the system, which is a bicycle. The emergent behavior is we have transport. Or they can be negative. For instance, in engineering, dissimilar metals and mechanical engineering can cause corrosion when they're put together. And that's a negative emergence that you might not necessarily realize unless you have the understanding of those components and what other materials they're touching. So we also need to design and optimize that system as a whole. So rather than taking those components in isolation, we want to look for best system performance and how to design those components for the system. If you think of an electric vehicle as an example, and you speak to the team manufacturing the battery, and say we want to increase the range of this vehicle, they might want to put in a much bigger, heavier battery, but that has an overall impact on the system by increasing the weight and potentially reducing the maximum speed. So these trade-offs have to be made at the right level within the system. And to apply that whole systems thinking, we need to look at the different views and different perspectives. So understanding the wholes and the parts of the system at the same time and keeping that in our minds. And that's looking at the external environment, the system boundary, so where does our system end and that environment start? And what are the interfaces as we go across that boundary? How does the system interact across the boundary? And how does it relate to the environment? We need to look at the internal architecture, so splitting the system down into component blocks, how they relate to each other and how they produce that emergent behavior. And look at those individual component parts, their boundaries, interfaces, and also the allocation of resources like power across the system, the weight of different components, and how they're allocated to the different parts within the system. So a systems thinker considers the different perspectives of the stakeholders as well. So that will be looking at the end users, maintainers, installers, buyers, manufacturers, and looking at how they relate to the system and what their perspective is when they look in on that system and how to use it. And very importantly, we also need to look at feedback loops. We need to look at the system dynamics here, how the system responds to different stimulus, whether that's external stimulus, or in the case of safety engineering, what happens if one of the components in the system fails, and how does the system respond to that? Does it flag it? Does it take over? Does it fail in a bad way that could cause an accident? And by analyzing these feedback loops, we can apply that systems thinking and look at those what-if situations. To give you an example of systems thinking here, we can look at something which is quite common now as LiDAR systems. So LiDAR is a time-of-flight mechanism. It bounces a laser beam off an object, and those photons take a set amount of time to travel to the object and travel back to a photodetector of some sort. So we see LiDAR in things like the iPhone 12 Pro here, where it's used for some of the photography, augmented reality, even mapping out your rooms for DIY. We see it in autonomous vehicles for self-driving and safety functionality. So if we want to apply some systems thinking here, let's look at the automotive LiDAR case, and we want to consider the difference between invention and innovation. So innovation is really solving problems that add value, whereas invention is coming up with the creative ideas. But solving problems inside that system's boundary is only useful when it adds value outside the system boundary. So the innovation here is solving the problems inside that boundary to add that external value. And if we look at the block diagram, we have some simple components. You've got your control and interface and your timing critically, a laser driver, the laser, some transmit and receive optics, your photodiode, an amplifier, some power management. All blocks where there's probably 1,001 ways that we could look at different and interesting improvements as engineers and solve some of the problems inside to that system. But how do they apply externally? And are they worth solving those problems, or is it just fun for us to solve some of them? Now, if you think of the external problems, one of the key things is cost, and a big way that you can reduce cost in these systems is looking at your scanning and optics, because the mechanical components there are expensive to manufacture. They also make the products much bigger on the vehicle and much more difficult to maintain. So that's a really good area for people who are wanting to solve problems, is looking at things like solid state scanning mechanisms, looking at alternatives to scanning and solutions like flash LiDAR, to take a whole frame at a time, and trying to eliminate the traditional mechanical scanning. Looking at another problem here is weather. So looking outside that system boundary and at the system environment, we can consider the fog, mist, rain, and we can solve that problem to some extent by switching the wavelength of light so it doesn't get absorbed as much by the water. And that means changing the laser and changing the photodiode. So also a really good problem to solve within the system, adds value by making that useful in a much wider range of environmental conditions when you're on the road. But some problems we can't necessarily solve within a system. The fly here is a good example as you're driving down the road and they get stuck to your windscreen, and exactly the same happens to your LiDAR system. So we need to consider that problem and what we can do about it. We might be able to detect when the front of our LiDAR is dirty by looking at how much light is reflected back or whether we no longer get a signal. And we might be able to flag that up at the vehicle level to say do something about that. Whether we can do something ourselves is unlikely, but you can look at solutions within vehicles like, for instance, headlights now often have a windscreen washer system to clean them, and it's likely that similar systems will be in use for LiDAR at that vehicle level. So looking at how we discover requirements, there's a whole series of techniques that we can use. The first thing we need to consider is who are the stakeholders. So we want to look beyond the first stakeholder people think about, which is their existing customers. And we want to look at potential customers, different users of the product, the buyers, the suppliers. All of these people are the sort of soft side of stakeholder management. And these are a really common set of stakeholders. We also want to look at standards like safety, electromagnetic compatibility, security, some of the automotive standards in here. We want to look at government regulations, so things like how we dispose of the product, ROCE, and some of the other directives. And we want to look at some of the internal stakeholders, so that can be your design, manufacturing, support and operations. It could be coding standards, internal processes and policy, and some of the requirements that come from the business. So what's the time to market? What's the risk appetite that we have? What's the expected return on investment? Once we've identified who the stakeholders are, we need to start looking at how to discover the stakeholder requirements from them. So there's different techniques that we can use, and there's probably too much to go into in detail here, but there's 4 key areas. The first is from the design industry, which is what we call design thinking. So that's trying to empathize with your stakeholders and really understand what their problems are. It can involve doing interviews, focus groups, going out and shadowing them in their jobs to understand how they use systems, building user stories, as we often see in the software industry, that describe how that system is operated, how that system is applied, and what the needs are. And building diagrams, so that can be process flow diagrams, it can be looking at the customer journey as they use that system, and how that system works within that environment. We can use the systems thinking techniques that we've talked about earlier, so looking at different relationships, viewpoints, perspectives, patterns, defining the system's boundaries and the different distinctions, looking at emergent behavior, and what we call whole-ons, so looking at that system as a whole and a part. We can apply traditional product management techniques, so win-loss analysis, looking at which of our products were successful and which weren't, and why that happened, and also the competitive landscape, and win-loss analysis for some of our competitors' products if we can. We can describe these market problems, we can look at roadmaps of the problems and at what point we should try and solve that problem and when it has the most value for us. We can do technology readiness and technology assessment, looking at what technologies we have already and at what stage and readiness they're at. And we can start building personas of users, buyers, and other stakeholders. So looking really at the people, who they are, and what their needs are. And we can also do agile and lean methods here. So prototypes and prototypes. A prototype is something that doesn't really have any functionality other than testing the product. For instance, when the early voice recognition systems were put in place, it was actually a team of people typewriting in another room to see what the experience for someone would be when text appears back on their computer screen. The software had not been developed at that point. Prototypes as well, if we can do any early prototypes in electronics, that might be a software version, a model, an FPGA, anything we can do to take back to the customer, test out that concept, and elicit more requirements. Once we have enough built, we have a minimum viable product, which we can release to market at the earliest possible point. It might not have all the features, but it satisfies enough to solve a key section of those products problems and to be able to learn more about that system by releasing that and seeing what the market feedback is. And that's really an iterative approach to development. What we also need to consider is when we discover these needs, do our stakeholders tell us everything? So think about when you order a coffee. What do you ask for and what don't you ask for? Typically, you'll ask for milk, sugar, you might ask for a particular variety of coffee or a style of coffee, but you're unlikely to ask for the plastic cup. You're unlikely to specify the temperature it's served at. You probably won't ask for good service, although you'll expect it. And this is a whole series of unspoken requirements that they are implicit rather than explicit in the needs that people have. And stakeholders only tend to specify what matters to them, so these unspoken requirements are often forgotten. They're overlooked, they're often essential because they might be very basic, but they're critical to the operation of the systems, and they're needed to ensure a successful outcome. And we need to manage them in the same way that we're managing the requirements that people do tell us about. And by recognizing and filling those gaps, we have a better system. So a lot of these requirements relate to safety. For instance, if you go and book a meeting room, do you ask for fire extinguishers? Probably not. You expect them to be there, you expect them to meet the standards that are required for a building, and the only time that you'll actually care is if that building sets on fire and you need to get out of there. But if you were the person designing that building, you would have to specify that there were fire extinguishers because someone needs to go and buy them, they need to install them, and they need to maintain and service them, even though they may not immediately be obvious to your stakeholders to look for those fire extinguishers when they're actually using that building in the end. To summarize, we need to look at the early focus of a project, and that should be on the market problems. We need to understand the market problems in detail before we start the design, prioritize the problems that are urgent, pervasive, and valuable. Our systems thinking delivers a context and understanding for that system. It's looking at the boundaries, the interfaces, the different relationships and perspectives, and the emergent behavior of that system. And we use that information to guide the design as we go through the design phases. Our requirements are the language on which the systems are built. So we need to remember that there's multiple stakeholders, document the problems as formal requirements that can be validated against, consider those implicit requirements that aren't communicated, and check them with the stakeholders to make sure that our understanding is correct. And remember that specifications describe the solution and requirements describe the problem. If you've got any questions or would like to get in touch, my email address is here, and I'd be very pleased to hear from you. Thank you for your time.